Okay, hello everyone. Welcome to our webinar. Today we have Dr. Chris Packham here to talk to us about the James Webb Telescope and show us some images and talk about the telescope itself. Welcome, Dr. Packham. Thank you so much for doing this.
Thank you so much, and thanks for hosting me. And yeah, it's a pleasure to see you all. As was mentioned, I'm a professor in the Department of Physics and Astronomy here at the University of Texas San Antonio, and I'm really enjoying using the James Webb Space Telescope, which I'm going to end up calling the JWST. So forgive me if I use that acronym pretty fast. And I wanted to just show some really cool pictures and a little bit of background information about what's making the JWST really such an amazing facility for astrophysics. So in order to start with that, what I'm going to do is show actually a little video. This is showing the JWST. This is an artist impression of what it looks like out in space. The blueprints, of course, in the background, some images taken by JWST also in the background. Here's the primary mirror of the JWST. Looks like it's looking at some galaxy, maybe our own galaxy by the look of it there. And here is the so-called sun shield. This keeps the telescope cool and in the shade as it's so far away from the Earth, about 1 million miles away from the Earth. We have to make our own shade. So just like a sun umbrella or a parasol, it has its own umbrella to keep things cool and dark. That's what this big sun shield is. This is about the size of a tennis court. It took about 20 years and about 20,000 engineers and scientists around the world to develop the James Webb Space Telescope, and it's working better than designed. So it's really, really cool. And what I wanted to do is start off by showing a video. This was actually a trailer that was released just before the launch of the JWST by NASA. And I think it shows really wonderfully and discusses really wonderfully why it was such an exciting time to see this thing launch. So I'm going to go across the video now, narrated by Carlos Sagan.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
So it was always going to be pretty exciting as we launched it. But why when we've got the Hubble Space Telescope? Well, here's a kind of a comparison between the two telescopes. The Hubble Space Telescope over here on the left, this is about the size of a school bus. And over here we have the James Webb Space Telescope. This sun shield is about the size of a tennis court. So there's some things there that show that it's a little bit different. So for example, the mirror has a diameter on the Hubble of about 2.4 meters, about 8 feet, whereas the mirror on the Webb is about 6.5 meters, 21.3 feet. So that's one of the most immediate differences. And let me show you that again. Here they are to scale with the primary mirror as shown in the Hubble and the James Webb Space Telescope. And here's a person standing next to the Hubble Space Telescope. Primary mirror, the part that does the collection of the light, compared to the JWST. So you can see that the mirror is much larger on the JWST. So that's one thing that shows why it's became such an exciting telescope. And if you look at the size of them, again, 2.4, 2.5 meters compared to 6.5 meters. And the amount of light that we collect is related to the area, which is simply pi r squared. So JWST collects about 7 times more light than the than the Hubble Space Telescope. So that often leads people to say, which is better, or does that mean JWST is just a better telescope? I think that question's kind of invalid. Let me explain why. Here's the electromagnetic spectrum, the light that we can see all the way from the gamma rays over here on the right, those very energetic, through X-rays, ultraviolet, this is visible that we see with our eyes, infrared, microwaves, and over to the radio waves. Then if we superimpose here, this is the type of light that the Hubble Space Telescope sees in this little blue box. You can see it's mostly confined to visible, a little bit of ultraviolet, a little bit of infrared. Here's what the JWST sees. You can see it's mostly infrared. So which is better? Well, they're not really comparing like to like. They complement each other. They support each other. That's why it's so exciting to have both the JWST and Hubble in orbit simultaneously. It's a really, really exciting time. So why is the JWST focusing on the infrared? Well, infrared gives a different view. Let's imagine a terrestrial example, an example here on the Earth. Let's imagine you've got a first responder, a fire person going in to try to rescue someone. Let's imagine this firefighter is searching for someone on the floor. Now, if this firefighter, if she's looking around in this smoke-filled room, she can't see through with her own eyes because you can see that it's smoke-filled and the smoke is making things difficult to see. If we switch to infrared, that means we can see heat. This is a heat map. So here's the heat coming out of the firefighter, and here's the heat from someone lying, waiting to be rescued by the firefighter. In this case, the firefighter, she can easily recognize them and go and rescue them. Which is better, optical or infrared? Again, the question's really invalid. It's better to have both. That's the real secret of what we really want to do, have both infrared and optical wavelengths. So to extend this a little bit more, here's some warm-blooded animals, some like meerkats over here on the left, and here's a crocodile, as its teeth are on the outside. This is a crocodile on the right-hand side. This is a cold-blooded animal. This is a warm-blooded mammal. So if I switch to the infrared, what we can see is those warm-blooded things are nicely glowing in infrared, and this cold-blooded reptile, this needs to be heating up and basking in the sun. That's why it does that. So it's producing a little bit of infrared, but not nearly as much as those nice warm meerkats there. So the same is true as we think about observing the universe. Astronomy is a kind of unusual science in the sense of we can only observe something. Other sciences, for example, physics, we can smash something up and take a look inside. In biology, you can inject the cell with a dye. In chemistry, you can set fire to it. In astronomy, we can only look at it, and often we can only look at it from one vantage point. In this case, this beautiful image of the Whirlpool galaxy, it's millions of light years away. So we can only look at it from one viewpoint. So what astronomers have to do is look at it at radio waves, infrared, optical, ultraviolet, X-ray, as many wavelengths as we can in order to try to piece together what's going on there. Only that combination of wavelengths is what allows us to make the progress to understand what's going on. So astronomy is a strange science in the sense that we can only do this. We have to use those different wavelengths. We can't touch. We typically can't interact. The solar system is the only exception to that rule. So JWST, what we do is we have this sunshade. Here's a little cartoon of what it looks like right now. Here's the sunshade. It's projecting to the sun, and the temperature is a nice toasty 122 Fahrenheit. So pretty warm. Even though it's in the vacuum of space, it's pretty warm because the sunlight is illuminating it. The backside is in the shadow. This is at a very cold, minus 450 Fahrenheit. So this is where we can make those observations. We can hide the telescope from the heat of the sun, from the light of the sun, and that allows us to make those very, very sensitive observations. So this is why we have this enormous sun shield to make that shielding really a crucial part of the whole observatory. If we look at those mirrors, here's those various mirrors. We don't just have one mirror, we have multiple segments, and each of those segments can be moved individually. So when the telescope was first launched, we had to unfold it and align these mirrors. And indeed, we have to keep them aligned. How closely do we have to keep them aligned? They're aligned to about 1/5000th the thickness of a human hair. This is done robotically from the ground. The telescope is about 1 million miles away from the Earth. So what an incredible engineering feat that we can do this with this telescope. It's really, really cool to see this. So the first images were unveiled not so many years ago. It's only like 2 or 3 years ago that we started to get the images from the James Webb Space Telescope. When those first images started to appear at the Institute of the Space, at the place that runs the telescope, we started to understand the amazing quality. So there was a very significant unveiling event, but I heard from someone that these are the most incredible images you've seen. And one of the things that really struck me is that one of the people in charge of the telescope said, when we look at the sky from the ground, we see stars, we see galaxies, and we see lots of stuff in between. When you use the James Webb Space Telescope, there's no such thing as blank sky. Let me show you what I mean by that. Here's actually one of the first images ever taken by the James Webb Space Telescope when it was fully aligned. It was just of a normal, boring star. Here's the star here. These lines, these spikes coming out of it. This tells us something about the alignment of the telescope. It's a thing of physics called diffraction. It shows that it's very, very well aligned. I can explain a little bit about that if you're interested at the end of this talk, but it's just an effect that's left over from the physics of how we put the telescope together. But this was a star that we wanted to make sure it was aligned. Everything else in this image is a galaxy. A galaxy is a collection of about 100 billion stars. Imagine how many stars we're seeing in this single image, which is purely a quick snapshot to make sure that the telescope's fully aligned. Just incredible to see how this thing is operating. And why is this so exciting? I'm going to show you the previous best image taken from space, from an earlier version of a space telescope at infrared wavelengths of the same region. Here's the same star and the same region. Of course, you don't see any of those galaxies in the background. This is the power of the James Webb Space Telescope. So we knew that this was going to be an incredible facility and really a way to move forwards and advance astrophysics in a fundamentally new way. So let's look at some of the images that I have really grabbed me as we've seen these images coming out of the James Webb Space Telescope. What I'm going to do this is starting off in the local universe and go further away from the Earth. Here's one of the first images that I love, Jupiter. Here we can see these really kind of strange looking, not the type of Jupiter not the image of Jupiter that we're used to seeing. What we're seeing is the infrared. So what we look here, we can see the atmosphere, we can see the clouds in the atmosphere. And actually what's going on is the brighter ones are the warmer ones, the darker ones are the cooler clouds. So just like on the Earth, at the top of the atmosphere, it's pretty cool. As you get towards the ground, it gets warmer. So the same thing is going on in the cloud decks of Jupiter. So in this area where I'm highlighting my fake laser pointer, this is a little bit brighter, so this is a little bit deeper in. The dark areas a little bit further out. So immediately we can get an idea of the three-dimensional nature of Jupiter just by having a quick look at this image. There's some hidden things here. We can see the rings of Jupiter. We can see the aurora, a northern aurora, southern aurora of on Jupiter. We can see a couple of the moons of Jupiter just in this single quick image. But I want to zoom in. Wonderful image of Jupiter. And the thing that I think is really pretty obvious is this thing. This is the great red spot. This is a storm that's been going on or within the atmosphere of Jupiter for over 400 years, first detected by Galileo. This is incredible to see this. So really, really cool to see this. We would fit multiple Earths within this single storm. It's something like, but not totally the same as a hurricane here on the Earth. Let's go off to Saturn. There's a wonderful moon of Saturn called Enceladus or Enceladus. So this is a moon that has an icy crust on the surface, but underneath it there's a water plume. You can see water kind of jetting out, just like a geyser or a geyser here on the Earth. You can see this light water venting out into space. And what Webb saw is we could trace that plume of water out to a very large distance. Now, one of the reasons why I find this so exciting, this plume of water extends about 20 times the size of Enceladus. And what we know is anywhere on Earth, there's life. Anywhere that there's water on life, sorry, anywhere that there's water on the Earth, there's life. Could there be life up there? Could be. In the plume, there seems to be organic compounds, which are the ingredients for amino acids, which are the building blocks of life. So I'm really excited to see this. I think it really encourages us to think about putting a space probe up there. Nothing planned right now, but I hope that we will do that in the not too distant future. What's happening is this water is being kind of ejected from Enceladus, and we see a torus, a donut shape of water in orbit around Saturn, much further than the rings of Saturn. So really, really cool to think about seeing this. We can also look at Uranus. Uranus, we see this beautiful disk here. The North Pole is pointing directly towards the sun, and we see this beautiful ring system around Uranus. And finally, a wonderful image of Neptune. Here we can see Neptune here with the various clouds, storms, things similar to the Great Red Spot on Jupiter. And we see this beautiful ring system and a very bright moon of Neptune called Triton. So incredible images that we can see of our own solar system right off the bat, right in these very early period of JWST's observations. So one of the first images that was released was this image. This is called the cliff. Some people call it the cliffs of creation. What's going on here? Well, what we're seeing is a stellar nursery, a nebula. Stars are forming within this dust cloud. So in this kind of orangey red cloud, parts of this cloud are collapsing down, forming new stars, perhaps forming new solar systems there. And these stars start to heat up and they start to produce light and energy of themselves. Outside this dust cloud, we can see these stars have emerged from that dust cloud and they're heating up the surface. And we can see this beautiful kind of bluish color. This is evaporation of the surface of this nebula because of these hot, young, new stars evaporating parts of the surface off there. Now, just like I showed with that firefighter when she was looking for the person on the floor, the stars that we're seeing here, we can't see them with the Hubble Space Telescope or optical wavelengths. They're hidden in the dust cloud. We can see straight through this dust cloud using the James Webb Space Telescope, and that's what allows us to see these stars for the first time. Really, really, really incredible. I'm seeing a question. Could you talk a little bit about the refraction in JWST's picture and what they mean? Can you, I'm not sure I follow your question about refraction. Did you mean diffraction, Esha? Okay, so diffraction. So you can see these spikes here, just like I showed in that early image. So diffraction is an effect that happens. I'm going to go back to a picture of the telescope. Diffraction is an effect of the telescope, of the light as it comes in through the telescope. If I get looking for a picture of the telescope, so let me find one. Okay, so if I've got a picture of the telescope, you can see the light hits the primary mirror, this yellowy color, then reflects off onto a secondary mirror, and then it reflects back into the through a hole in the primary mirror, and then we capture the light with a camera, just like our iPhone or Android cameras. Now, these spikes are created because of these support structures that are holding the secondary mirror. It's reflecting and kind of, or a special term in physics called diffraction, which is the interaction of light with these three struts that are holding the primary mirror, the secondary mirror above the primary. I hope that answers your question there, Esha. Did that address your question, Esha? Perfect. All right, so let's go back to this nebula. Wonderful image, really, really cool. So this is stars that are being born and new stars, maybe new solar systems. Let's go to the other side of things and let's look at stars that are dying. Here I've got an image taken by the James Webb Space Telescope. We've got, this is the star that's dying. It's puffing off its atmosphere out into space. And what we can see is the atmosphere is moving out. We can see this puffing off in various periods of time. It's expelling a large ring, and then it becomes quiet again and expels more out. So the further we look away from the star, the further we look back in time when that dust was expelled. And we can see there's a lot of structure here. On the left side, we're looking at the so-called near infrared. On the right side, we're looking deeper into the infrared, into the mid-infrared. So this tells us about the structure of this star as it's dying. Now, one of the things that I love with this image is that we can see both the near infrared and the mid infrared. But the thing that struck me is when this was first being unveiled, I could see this little structure. If I look here, we can see a structure, this linear structure here. This is actually a galaxy. All these other things out here are galaxies. There is no such thing as blank sky when you use the JWST. There is a huge number of galaxies out there. So, Somya, I see your question there. I will come back to answer your question at the very end of this talk, if that's okay, because then I can continue on with the science and come back to the physics of how we construct these images. So here's another much more recent image. This is an incredible image. Again, you can see these six figures here. That's because of the spikes of the diffraction spikes that are coming off of that secondary mirror or the support structure of that secondary mirror. And we can see this beautiful nebula. Again, it's a star that's dying, puffing off its atmosphere. But this star is going to go supernova. It's coming soon. When I say soon, anytime in the next few thousand years. Really, really cool to think that this will go supernova. What would it look like soon after that? Well, if we're still around to see it, this is what the supernova would look like about 36 years after the supernova has occurred. You can see this cloud of gas and dust being expelled out into the interstellar space. Incredible thing with a supernova is all of the elements, or many of the heavy elements that we are constructed from, both on the Earth as well as us, human beings, you and I, have been through a supernova explosion. So things like titanium, gold, anything beyond iron has been through a supernova explosion. So this is a really cool effect, amazing thing to think about as we look at these JWST pictures. Finally, here's another slow star death. I just love this image. The star puffing off its atmosphere, releasing it out into space. Just a beautiful, beautiful image. So again, star death, but let's be more optimistic. Let's go back to star birth. Here is just an incredible image. This is the Tarantula Nebula. What we're seeing here is, again, this gas and dust collapsing down to forming new stars. And we have a very tight cluster in the very center here. Let's zoom in. Here's a cluster of stars. There's so many stars here. It's evaporated a hole here, which allows us to see this with more clarity. It's burnt off. It's evaporated away the dust in this very central region allows us to seeing it more clearly. And if we switch to the deeper infrared, we can see this even with more clarity. We can see this dust and how it's creating these stars. So really, really cool. Now, one of the most famous nebulas out there is the Orion Nebula. Here's an image that was taken early on by the JWST, and let's compare that to what we see when we use the Hubble Space Telescope on the left, JWST on the right. So combining these images together, astronomers are getting a much better understanding of how stars form, how they evolve, and how the effect they have on the gas and dust around it. So the Orion Nebula is a beautiful nebula. We can see it here in Texas. You can see it at night now as we move into the winter period of the Earth's orbit. Really beautiful to see the Orion Nebula. But I think one of my favorite images of all time is this image. This is in the Eagle Nebula. This was taken by the Hubble Space Telescope quite a few years ago. It's used in many images. You see in science fiction things such as Star Trek, they use this several times. Here, what we're seeing here is the talon, the feet of the eagle, one of the eagle constellation. So these are the three talons, the feet of the feet of the Eagle Nebula, and we see these three pillars. Within each of these pillars, at the very tips, again, it's stars in formation. Stars are being created, potentially with solar systems there. So that's why it's called the pillars of creation, because we're making new stars, new solar systems in that area. Now, this is taken with the Hubble Space Telescope. Let's take a look at what it would look like when we viewed it with the James Webb Space Telescope. We can see through that gas and dust with far more ability than we could with just the Hubble Space Telescope. Let's view them side by side. What an incredible image. And it shows just how far we can see through the gas and dust when we look at infrared part of the spectrum. Beautiful to see those two together. And so I really love this image. And so let's take a look at what would happen if we animate this a little bit and just fade them in. Just love the ability to do this and play around on these images. What an incredible difference we see by looking in the infrared compared to the optical, and what a powerful technique it is to combine these two. Now, this image was unveiled at the start of this AI kind of surge in popularity. So one person used AI to remove all the stars from the JWST image. And this is a wonderful image with only the nebula. So the stars have been removed by AI. Again, we see only the nebula. What a beautiful image as we can see it here. Let's go back to the JWST real images. This is into the infrared part of the spectrum, the so-called mid-infrared part of the spectrum. What an absolutely incredible image. And look, we're just in just past Halloween, very close to Dia de los Muertos. So just for fun, this is just a coincidence, just what human sees. But if we look in here, it does look very kind of spooky. It does look like a human face, well, a human-esque face there. Similar to a human face there, or a gargoyle or something. That's actually incredible to see that. Okay, back to more sensible things. So one of the things that I've spoken about a couple of times is stars in formation and making up their own solar systems. Let's look at one of those. This is a star called Fomalhaut. What we can see is a star in the center. We've kind of removed the star. We don't want to know about the star. What we want to see is the disk of material that's in orbit around that star. What we can see is this beautiful ring. We can see an inner ring and some inner fuzz there. So we think there's a lot of gas and dust in the disk here, a lot of disk, a secondary disk, and a third disk, a tertiary disk out here. But for some reason, there's some gap here. Why is there a gap? Well, the way that we think stars and planets form is they rotate round, and just like the solar system, all the planets are in an arc. And if we think about the planets, let's think about Jupiter and Saturn, for example. Jupiter was probably one of the first planets that formed out of the solar nebula. out of the sun's nebula, and it started to gravitationally grab gas and dust. As it did that, as it was in orbit, it would have carved out an area where there was less gas and dust because it had all fallen onto Jupiter. So what we'd see is a disk with a kind of clearing there. That's what we think we're seeing when we look at this. There seems to be an area that something has cleared out all the gas and dust. Perhaps it's a planet that's in formation that we're seeing here. What an incredible image that this is. This is only the edge from the star to this outer edge is only about 14 billion miles from the star to the edge there. So very, very cool to be seeing this. Wonderful image to see. Let's go to an even grander scale. Let's go outside of our own Milky Way galaxy. Let's look at a wonderful image. This is something called Stephan's Quintet. This is 5 galaxies, so 1, 2, 3, 4, 5 galaxies that all look to be pretty close. Indeed, some of them are actually interacting. For example, these two are interacting. They're not actually all that close to each other. So when we look at look at the sky, look at the galaxies, actually some of the galaxies are much closer to each other than the other galaxies. Some galaxies are much further away. And that's what's happening here. Some of these galaxies are much further away, some are much closer to us. But when we look at them together, we can't get a full idea of the distance, so they all look to be almost in the same part of the sky. But they're actually, if we could see this in 3 dimensions, they would be much further away. Now, this is a very well-known set of galaxies. It's called Stephan's Quintet. One of them, this one at the top, has a supermassive black hole at its core. More about supermassive black holes here. But it's a really wonderful image. I love this image. But actually, I'm kind of lying to you. I'd said that there's 5 galaxies here, and I counted them for you. But really, I'm lying to you. Let's zoom in on just a little bit. Each of these objects, except for this very bright one, each of these objects is a galaxy. So if I go back to this image here, how many galaxies are there? Tens, maybe 100. And remember, each galaxy made up of about 100 billion stars. So this is just absolutely an incredible sight that we're seeing here. So let me go back to this galaxy. I study about supermassive black holes. So this is something that I want to talk to you a little bit about. Here's what I think is going on here. This is what my group and I are studying. Here is a galaxy, and in the very center, we've got a supermassive black hole gobbling up gas and dust, but some of that gas and dust gets ejected through winds and cavities and jets. Some of the area that's hosting the supermassive black hole has a diameter of only light hours across, yet the jets of material that are being ejected from the center extend thousands or hundreds of thousands of light years from the center. What do we think's going on? What do I think we're going to be able to see? Here's an artist's impression of what it would look like if we could really see the central region. Supermassive black hole encased in gas and dust, which has become extremely hot and so extremely bright. And this is the jets of material that are being squirted out from the supermassive black hole. And here we see this material that's falling into there. This is what I think we're seeing when we look at these supermassive black holes. Really, really cool. I'm going to show one more set of images from my group at the very, very end of this presentation. Here's another wonderful image. This is the so-called Cartwheel Galaxy. It's about 500 million light years away. What happened is there was a spiral galaxy that got kind of interacted with. A very fast galaxy went through the center of that spiral galaxy. Now, most galaxies, although they're made up of 100 billion stars, if a galaxy collides with another galaxy, actually very few stars actually collide. What happens is the gravitational effect of one galaxy passing through another galaxy creates a shock wave. And what we can see here, this shock wave is causing those nebula to preferentially to collapse. And so you get a shock wave of suddenly new stars being formed because of the gravitational shock wave going through the galaxy. So what we can see here is this outer edge, this ring, is a shock wave that's causing the nebulas to collapse. We can see a secondary shock wave reverberating in the very center here. So this is what's creating this beautiful, very rare ring galaxy. Love this image of the cartwheel galaxy. We can look at it deeper into the infrared here. We can see that shock wave in a different way. We can get rid of a little bit of the confusion from seeing so many stars. What an incredible image. We can look into the center of a galaxy called M74, the Phantom Galaxy. Look at the detail in the very center here. We think there's a supermassive black hole there with the gas and dust spiraling around it. And again, I want to illustrate the power of James Webb Space Telescope and Hubble. Here's Hubble on the left, James Webb Space Telescope on the right. Here's the combination. This is where we can really get to the science by doing this combination. Again, let's look at that. What a wonderful, beautiful image that phantom galaxy really is. We can see other beautiful galaxies. Here's a so-called New General Catalog NGC 1433, just another spiral galaxy on the outer edge, and it almost looks like a mini spiral encased in the center. Beautiful, beautiful image. Another beautiful image of a whirlpool galaxy. Look at the detail here. Incredible to see what we can see with the James Webb Space Telescope here. Now, these are individual galaxies. One of the first images unveiled to President Biden was of this cluster of galaxies. It's got a strange name, SMACS 0723, but it's a cluster of galaxies. Everything that doesn't have these spikes, these six spikes. So everything but this object, this object, this object, this object, of these objects along the bottom. Everything here is a galaxy. Again, a collection of 100 billion stars. So we see a huge number of galaxies. The area of this image on the sky is equivalent to a grain of sand held on the tip of your finger extended at arm's length. So you can imagine if this is typical across all of the universe, how many galaxies there truly are out there. So I just love looking at this image. And this is cool, thinking about just the number of galaxies, but there's something weird going on here. So this is the center of this cluster. This is a very, very massive cluster. Lots of gravitational effects going on here, but this is the center. Now, gravity actually bends light. It can act like a lens. So I'm wearing glasses, so I've got some lenses that's helping my eyes focus on my computer screen. So we can have a gravitational lens that's created by the immense gravity of a galaxy. Now, the lens isn't well formed. It's not kind of created in the same way as my glasses are created. So the lens is not very good. It's not very efficient. But what's going on is there's a very, very massive galaxy here. Behind that galaxy, a very long way away, is another galaxy, and it happens to be being lensed. If you look here, you can see some curved structures. They're curved. It looks like the center of the radius of this curvature is over here on the center part. This is the gravitational lens of that very distant galaxy being lensed by this very massive galaxy. And so it focuses the light, and it actually allows us to see things even further away than we could have been able to see it otherwise. So a gravitational lens is an effect first predicted by Einstein, proved 20, 30 years ago, but now a way that we can use this kind of strange effect of gravity to see even further away in these images from James Webb Space Telescope, and it's used on ground-based and Hubble Space Telescope images as well. One more image just to illustrate this incredible detail. look at this strange thing here. This is a warped image of a galaxy. This is actually much further away than this object, but this object is very massive, and so it's creating this warping and creating this warped image. What a cool thing to see. Finally, let's go to the very distant universe. Here's another galaxy cluster. Again, each of everything here is a galaxy, 100 billion stars. So what we can see is the very earliest galaxies. And this shows that galaxies that only about 650 million years after the Big Bang are very much out there and very much formed. And this is very surprising. We didn't expect to see this. We're trying to understand what this means. This is an area of extremely active research within the James Webb Space Telescope community. We can't explain how those galaxies formed so quickly. So this is something that's really cool. So here's how we thought it works, that stars form and galaxies assemble. They begin to change the gas and dust around them, transform that, and eventually the universe becomes clear. We're trying to understand this. Our models are being challenged by these new observations. This is, again, an area of very active research. One more cluster, just because I like it. This is just a beautiful image. If we zoom in to this panel here, A, you can see this incredible gravitational lens here, and there's another incredible gravitational lens here, really wrapping this galaxy almost around this lensing of this very massive galaxy. Really, really cool stuff. So just a very quick couple of comments about the stuff that the folks that I'm working with, the so-called GATOs, the Galaxy Activity Torus and Outflow Survey. Here's an image taken by the Hubble Space Telescope of a galaxy called NGT 5728. Here's what it looks like in the very center region through the James Webb Space Telescope. And we're using advanced image processing techniques to even improve this. So it's a really, really cool thing to do. So we're actually already designing the next generation space telescope. This is the Habitable Worlds Observatory. I'm on the team that's helping to design this, hoping to launch in the 2030s to 2040s. And I think the exciting thing is our generation is the first generation in history to have the formidable technology to prove the existence of life on other planets. So this telescope being planned by NASA is the first NASA mission to explicitly search for the presence of life on planets outside of our own solar system. So this is really cool. We're thinking about using all the knowledge that we learn in how to build the James Webb Space Telescope, how to operate it to make this next generation observatory even better. So very, very exciting times. I'm thrilled to be an astronomer at this period of time. So with that, I'm going to say thank you. There is a QR code to my homepage. Feel free to follow that. I'm going to take a couple of these questions right now. So let's see. I'm going to go back to showing an image of the JWST. So the first question is, why does the big mirror have to reflect the light onto the smaller mirror before hitting the camera? Well, so here we have the primary mirror. This is 6.5 meters across. The secondary mirror, about 1 meter across. And then we put all the instruments at the back here. So at the back, we have all of this real estate, about 6.5 meters of real estate in the background. So we've got a lot of stuff. We can pack in a lot of cameras. If we put all the cameras here, then they'd block the light going onto the primary mirror. We simply wouldn't see it unless we had very, very compact cameras, but then we can only have 1 or 2 cameras. So we think it's always better to reflect the light from that secondary mirror back through that hole and then to these sophisticated cameras at the back. I hope that answered your question. Does the color in the dust affect how many stars are being created in it? So each of the colors of the nebula corresponds to a different element. So I'm going to go back to this wonderful image here. The images here, if this was an optical image, which this is not, this is infrared, but if this was optical, then hydrogen and helium glow at a particular color, a kind of reddish orange color. The color oxygen glows a kind of particularly green color or blue color even. Copper glows at blue as well. Sorry, green. Sorry, green. So depending upon the colors, we can tell what elements it's made up of. We're very familiar with this actually in normal everyday life. Fireworks, if we want to have a particular color in a firework, we put a particular element in the firework, and that's what makes the colors that we see. What would you say is the most interesting part of your research? I think one of the coolest things, I think there's two areas. One of the coolest things is trying to understand supermassive black holes in the centers of those distant galaxies. And then the second part is, are we alone in the universe? How are we going to find life? How are we going to detect it? And what will that mean? So I think those two questions are the areas that interest me most. Any other questions or comments, anybody? Awesome. Zhen-Zhu, I'm going to hand back to you.
Thank you all so much for coming. Thank you so much, Dr. Packham. This was really amazing. It was amazing to see all these different images. I often like go onto the James Webb Telescope, like the little gallery that they have of the images that they release, and being able to see all these additional ones that you were able to show was amazing.
Awesome. Thank you.
Yeah. Thank you everyone for coming. Thank you, Dr. Packham, so much for hosting this webinar. Um, we're gonna end it here, and thank you all for coming again.
Thank you. Bye-bye.
Bye.